Hi, my name is Alex Pham, and this is my partner.
Hello, you guys. My name is Oscar Benitez. Thank you for being here with us this morning.
And we are going to present our 32-bit MIPS processor that we named SRF.
All right, so let's get to our agenda. So first on our agenda, we're going to explain why we named it SRF. And then after that, we're going to move on to our processor specifications, the enhancements we made to the MIPS processor, the enhancements verification, where we tested all the enhancements we did, and future plans and enhancements that we have for our processor. And Q&A is at the end, but at any point, you guys may ask questions as well. So what is SRF? So we named SRF after 3 characteristics that we thought our processor had. First one being simple. It's very easy to understand since it is a MIPS processor. It is reliable. It performs exactly when it's needed, and it does exactly what it wants to do according to the ISA. And it's fundamental. It's basically the baseline of a MIPS processor. So into our processor specifications, memory organization, we are using a Harvard memory architecture instead of von Neumann. So Harvard means that we have 2 memory diagrams, as you can see right here. It's separated from each other, unlike the von Neumann, which has instruction memory and data memory together. Both our memories right here are bit addressable, and they contain up to 4K bytes of data, and that also includes our I/O memory. So the way we organize the memory as well is big Indian format instead of little Indian format. Big Indian format, as you can see, we're starting with the value AF, FA0B05. So AF is stored in the lowest address, as you can see, it's stored in address A, and then we're incrementing as we move from most significant bit to least significant bit. We can see that FA is at address A plus 1, OB is at address A plus 2, and 05 is at address A plus 3.
So our machine register set consists of 32 32-bit registers, and this diagram contains the mnemonic name, the register value number, and the usage and the preserved on-call specifications. And the usage right here indicates how the registers ought to be used. However, when we use it in our processor, it's not strictly held to these purposes held right here. And the most familiar that you are probably most familiar with are the 0 register, which contains a constant value of 0 and which you're unable to write to. Stack pointer, which is at register 29, which is used to point to the stack data memory, and our return address register, register 31, which is used for our jump and link instruction when we want to save the PC to register 31. And next I want to talk about our flag registers. So we have 5 different flags. We have our carry flag, our overflow flag, our interrupt enable flag, our negative flag, and our 0 flag. And our carry flag indicates when an arithmetic carry has occurred in the most significant bits of the ALU, and following that is the overflow flag, which indicates when the sign result of an arithmetic operation does not fit inside 32-bit integer register. And then our interrupt enable indicates when the processor will turn on interrupt functionality, followed by our negative flag, which indicates when the result of the arithmetic operation is negative, and our 0 flag, which indicates when the arithmetic or logical operation is 0. And our processor classification data types, we have 2 different data types, and we have a 32-bit sign integer data type, which is able to represent a range of values between negative 2,147,483,648 to positive 2,147,483,647. So our second data type is the 32-bit unsigned integers, which can represent a range of values between 0 to 4,294,967,296.
So we have 4 different addressing modes. So the first one we're going to go over is the immediate addressing mode. As you can see here in our example, we're using an add immediate. We have an immediate value of 1, 2, 3, 4, 8, B, C, D. So in immediate addressing mode, we're using a 16-bit immediate value when we were using an I-type instruction. So add immediate is an I-type instruction. And when we're using a jump instruction, we're using a 26-bit immediate value. So in our add immediate, you can see that we're adding the contents of register T0 with the immediate value and storing it into register S0. So our second addressing mode is register addressing mode. So register addressing mode is when we're using two registers, of course. It includes 3 different registers, so it has RT, RS, and RD. So we're adding the content of register T0 and T2, and then we're placing that value into registers S2. So it has 2 types that use register addressing mode, our R-type instructions, as well as our I-type instructions. And then our third addressing mode is register indirect, which is used for our jump register instruction. As you can see in this example, it's basically just jump register to whatever address we have in this register right here. And it's commonly used to access operands in memory. Mostly used with our stack pointer, not our stack pointer, our return address in register 31. And then our fourth and final addressing mode is our base index addressing mode, which is commonly used for our load and store instructions. So in our example, we're using load. We're loading from register SA04, that address, and storing it into T0, or loading it. So our interrupt and reset. So our interrupt, the ways that our interrupt works is that our interrupt, so our I/O memory was going to send a request to the CPU. The CPU then sees the interrupt request, and then it services the request, and once it's done servicing the request, it sends it acknowledged back to the interrupt memory, and then the I/O memory, and then the I/O memory pulls its request away from the CPU. And then our reset as well, it resets all the values back to default values. So for our program counter, that would be a hex value of 0000000. Our stack pointer is a default value is 0000003F0. Our flags are all set to 0, as well as our 0 register, which is always a constant value of 0.
Okay, so next I'm going to talk about our instruction formats. So the first format I'm going to talk about is the R-type format. Since we are using a 32-bit processor, all the instruction formats are going to be 32 bits wide, and starting to the left with the 6-bit opcode field, this specifies the operation to take place for an instruction. However, since it's an R-type instruction, it will be set to 0 by default. And following that opcode field is the RS field, and the RS field is the 5-bit source operand register field. And after that is the second source operand register field, RT. And following that is the RD field, which specifies which destination register will be written into during the instruction. And there will be the champ field, which is the shift amount field, which is only used for shift instructions, and that is a 5-bit field as well. And lastly is the function field, which is an additional 6 bits to identify the operation. Since our opcode field is set to 0, our function bits will decide which R-type instruction will take place. The next format after that is the I-type format. And the I-type format, similarly to the R-type format, contains the 6-bit opcode field, which specifies which operation should take place, followed by the 5-bit RS field, which specifies the source operand register. And then following that is the 5-bit RT field, which is different from the R-type format in that it's used as a destination register instead of a source operand register. And lastly is the 16-bit immediate field, which contains a 16-bit constant to be used in the I-type instruction.
Is that signed constant?
It's not a signed constant until it gets signed extended from bit 15 onto bit 31. However, it's unsigned when you're using it with instructions like Andy, Ori, Louis, because we're only using 16 bits of this constant.
What about add immediate?
Yes, it's signed because we're doing a signed edition.
Okay.
And lastly is the J-type format, which is used for our jump instructions like jump and link. So once again, it consists of the 6-bit opcode field, which specifies which operation will take place, followed by the 26-bit address field that is used for the jump address calculation. So now we're on to our CPU block diagram. So in the CPU block diagram, we essentially have in this pinkish salmonish rectangle we have our CPU module and shows how it interconnects with the input-output module and the data memory module. So there's these three important buses right here, which are the control, address, and data buses. So the control bus consists of all the control signals that allow you to read and write from memory, and also the chip select function. And the address field specifies which address to either read or write from when accessing these two memory modules. And the data is the actual bus that is used to write to the memories. And in the CPU block, the control unit is used to provide all the control signals and control words for all the modules in there, like the instruction unit module and the data path module, and before, like I said, about the control signals for the input, output, and data memory module. And on the side over here, we have the interrupt request and interrupt acknowledge signals. So like Oscar was talking about before, the interrupt request signal would come from the input output module into the control unit module, and when the interrupt is complete, the acknowledge signal will be sent to the input output module, which will turn off the interrupt request. And the instruction unit module is used to provide the machine code for the instruction to be executed, and then that instruction register will be used to provide information on how the operands will be sourced in the data path module, along with how the ALU will execute using those source operands, along with at the end when you either write to the register file or write to your external memories.
So we're assuming that the CPU module connects to those buses? It shows it kind of floating there. So it looks like only I/O and memory talk to each other.
Yeah, it's very clear, but yes, it's assumed that the control unit and all the other modules within the CPU, and the CPU at the top level connects to these buses.
Okay.
Okay. And following that is our integer data path block diagram. So starting at the top, once again, is our 32-bit registers, and next to that 32-bit 32 register file is the demux, and the demux is used to select which register to write to. And if you go below that, there's the smux and tmux multiplexers that select which input to take in to load into our RS and RT registers in order to source our operands, which will then flow down to the ALU, which will perform our arithmetic logic unit instruction computations that need to take place, which will then get loaded into these registers below, which are used to either write to either the register file or the program counter, or say use ALU out as an address to access the memories.
Right, so our enhancements are, as you can see, we added this smux right here to allow us to pick from register 29 and our S out, which is our S address. So we're using this to increment and decrement our stack pointer accordingly. And we also included a shamp field for our ALU, just for our shift instruction, so we have the capability of shifting by a certain amount contained inside a register. So let's move on to our enhancements. So we have 10 enhancements. 3 of these are input, red eye, so input, output, and red eye. Those are the 3 that were included in the baseline of our MIPS processor. And then the ones that we came up with were rotate right with no carry, known as ROAR, rotate left no carry, roll, absolute value, which is AVS, decrement and increment, so dec would be dec, and then increment would be increment. We have a modulus, which would be mod, move, which is MOV, clear would be used as clear. So getting into the enhanced instruction input, it would be that you can see up here is the way the input instruction machine code is set. So it's basically just used to load a register value from input and output memory. That's the only capability it has, and it's the only restriction it has. So you can't load from our data memory or instruction memory. And here's an example of how it's used in a MIPS assembly code. It's input, the register you want to load it to, and the address it's coming from input and output memory. Then output instruction is similar to our input instruction. The only difference is that it stores a value into our input and output memory. So The only restriction is, of course, that you can only store into input and output memory, so all the other memories have denied access. And as you can see in our MIPS assembly code example, output takes in whatever the register of coding at AST1 and puts it into the location and input and output memory of T2.
Go over that again. I think you might have got that wrong.
Oh, output would take the contents from the memory at T2.
You're outputting from the CPU.
Yes, so it's outputting to this address location
Yeah.
from the memory within the register
Yeah.
and from the CPU.
Okay.
Sorry about that.
That's all right.
And then our return from interrupt instruction is used along with our set from interrupt instruction. So it allows us to return to the address prior to the interrupt request. So that means that all status flags at the program counter prior to that request will be popped off the stack and then assigned the current values of the present state flags and the program counter. So this instruction can only be used after you use a set from interrupt instruction known as a set IE.
So another one of our enhanced instruction is the rotate right instruction, which is just shortened to ROR, which is used to rotate to the right once without a carry bit. And so what happens in this case is the least significant bit is shifted out from the register and put into the most significant bit location of the register. And then, so if we were to use this in assembly, this is what it would look like. So it would be ROR for rotate right, T2, comma T0, meaning that we would rotate the value in T0 to the right and store that value into register T0, and T2.
So shift amount can never be included.
Due to our time constraints, we were unable to include that for this instruction, but if we were to enhance instruction more, we would most likely add that.
For the other baseline MIPS shift and or logical shifts and arithmetic shifts, did you do a barrel shifter? Because you indicated you could include the shift amount there to the ALU.
Yes, we did include a shift by amount, but we weren't sure if it was actually a true barrel shifter.
So you just implemented something in Verilog?
Yes.
And how did you do that?
So what we had was.
Do you have a slide later that's going to show us that?
No, but we do have our instruction memory and how we use our shift instructions and how the output is in the register dump. So
Okay.
we had to have that verification.
Yeah, okay.
And then following that is the rotate left instruction, which is similar to the rotate right instruction, except in this case you are shifting the most significant bit to the left and then putting it in the least significant bit location. And then if you were to use an assembly, it will be roll T2, T0, meaning that you would shift T0 out and put that bit into the least significant bit location and then store that value into register T2. And then like the rotate right, it's not affected by the shift amount. And then next is the absolute value instruction, which is used to get the absolute value of the source register. So then the way we did this is that we checked the most significant bit of the register, and if it was 1, we negated the register. And if it was 0, then we just kept it as it was because the number was already positive. And if we were to use an assembly, once again, we would just do APS, meaning that we get the absolute value of T0 and store it into T2. And then following this is the decrement instruction. So although we had decrement in our ALU, we weren't really using it. And so we decided to just add that in as an instruction to be able to use it. I know it's possible to also use add immediate -1 in order to do the same. So in a sense, this is kind of an alias.
But is it really an alias, or are you actually using resources to, in your state machine to carry that out? In other words, are we paying for this? With states, etc., and it's part of our silicon is going to be used to decode this instruction, and
yes, we didn't have to add a state.
so I was thinking with all of these inc, dec, clear, move, we don't want to pay for that. That's the idea of a reduced instruction set computer. Why pay for it when there's instructions that allow you? I can clear a register by subtracting 1 from itself. or I can move one with 0 register. So in other words, we don't want to pay for things just to have instructions that we throw out there. Anyway, go ahead. But that's the reality. That's reduced instruction set is reduce it. We pay for what we need. We don't just put things in there unless they're really aliases. In other words, that gets actually decoded by the assembler into an add immediate with a -1. Then that's okay. But to use resources for instructions that can already be done with the instruction set, that doesn't make any sense. Sorry to say.
Oh, that's fine.
Yeah. That's what we're here for though, right?
Yeah.
Yeah.
So our decrement instruction is used to decrement the value of a register by 1. So what essentially is happening here is that we're subtracting the value in source register RS by 1 and stores that difference inside the destination register RD. So if we were to do this in assembly, it would be decrement T2, comma T0, meaning that we would decrement T0 by 1 and store that value in T2.
Okay.
And then, of course, since we have decrement, you have to have increment. So this is used to increment the value of a register by 1. So this adds the value of source register RS by 1 and stores the difference in the destination, or not the difference, but the sum of RS plus 1 into the destination register RD. And the MIPS assembly code for that would be increment T2, comma T0, meaning that we would increase the value in T0 by 1 and store it into register T2.
So then we have the modulus instruction. So the modulus instruction is used to store the remainder of a division operation into a register. So in our MIPS assembly code, you can see that we're dividing T0 by T1, and the remainder of those two values would be stored into T2. So we can only use modulus we're using 2 registers. So of course we can't use 3 registers, we don't have that operation. And then an immediate value can also not be used when doing modulus.
Again, I was under the impression that our divide instruction already did the remainder into the high register.
Yes, it did do the divide instruction, but
So-
then this actually loads the modulus into the register file, whereas a division just stores it into the high register within the integer data.
Okay, good.
Then our next instruction is a move instruction. So it basically copies the value of one register into another register. So we're copying the value of T0 into T2. And only register values can we move. So we can't move any immediate values using this instruction. And then we have the clear instruction, which is used to clear a 32-bit register by assigning its values to 0 by clearing every bit in the register. And then we are clearing register T1 here in this example. And then we don't have any restrictions of what registers we are allowed to clear.
So this is our segment about the enhancement verification. So in this first part, we wanted to verify that our shift by amount functionality was working since it wasn't verified prior to this senior design project. So our first step right here consists of loading a 32-bit value into register 1. So I'm loading A, B, C, D, E, F, 0, 4 to register 1, as you can see right there. And following that, we did a shift right logical of register 1 by 2 and storing that into register 2. So as you can see, that value A, B, C, D, E, F, 0, 4 became 2AF 37 BC1 in register 2. And following that, we did that same shift by 2, however we did a shift to the left. And it makes sense that if you shift right a register twice and then you shift it back to the left, that the values should be the same again. So that's why in register 3, it contains the same value as register 1.
Unless you shift a negative number,
Yeah.
then it's
And
not
then-
the same.
And then there's the SRA instruction, which we did a shift amount by, and it's different from shift right logical because we're shifting the value of the most significant bit, which is why when we shift the value in register 3, A, B, C, D, E, F, 0, 4, it becomes EAF 37 BC1, which is different from the first time when we did a shift right logical.
And then we get to the part of where we verified our enhanced instructions. You can see right here. We load the immediate value of C0C 00000 into register 5. And then, as you can see over here, register 5 has that value that we just loaded. So we start by rotating right the contents of register 5 and storing it into register 6. So we rotate C to the right. Of course, it becomes a 6. So you can see here it becomes a 6, 0, 6, 0, 0, 0, 0, 0. And then we rotate it to the left, the contents of register 6, just to double check. And as you can see, it holds the value of register 5 and register 7 as well, just to verify that we are shifting correctly. And we took the absolute value of register 7, and then since C is a negative value because it has a 1, it's the most significant bit, when we took the absolute value of that, we got 3F4, 0, 0, 0, 0. And then we decided to decrement that instruction, so 4 minus 1 of course becomes 3, so you see 3F here to show that we decrement it. And then we increment it once again to go back to the original value that we had at register 8. So as you can see, register 10 and register 8 both have the same values, just to verify that we're doing all our instructions correctly.
And then following that, we loaded the immediate value of 3F3, F into register 11. And after doing so, we tried doing our modulus instruction, where we divided register 10 by register 11. And as you can see, register 10 contains the value of 3F4, 0, 0, 0, 0, 0, and we're dividing it by 1 less than that number. So therefore, if you divide a number by a number that's 1 less than it, then the remainder is going to be 1, which in this case it is. Because if you check register 12 in this case, you can see that the modulus is 1. And following that, we tried our move instruction by checking to see if register 12, the value in that is able to be moved to register 13, which it is in this case, because if you look at this register right here, it has the same register as the previous register, which is 1. And following that, we did a clear register 14. Prior to the clear, register 14 was undefined, so when we cleared it, it will set to all zeros.
So this was good that they were simple so we could actually see the verification. Did you do things more exotic like shift by 16 or, you know, so here was just shift by 2.
Yeah.
So, which is easy for the audience to see.
Mm-hmm.
But did you try something more rigorous with these instructions?
Uh,
Like remainders that weren't 1 or things like that? Just curious.
We didn't really try that. We just assumed that we were able to shift twice, then what's the difference between 2?
Yeah, you never assume. I mean, in real life, you never assume if I could just do it 2, remainders 1. You beat it to death a little bit. I just wondered if you had time. But this is good for
Yeah,
here.
that's why we chose these lesser operations, because we knew we had to present it and as well put
Make it
in
understandable. Good job.
And then talking about our feature plans and enhancements, obviously we'd like to pipeline our processor because it increase our throughput drastically, of course, because you'd be able to decode instructions, perform ALU operations, and also write to memory or the register file simultaneously. And we'd also like to add conditional branches. I know some other groups decided to do like branch, if overflow, branch, if carry, and other types of jumps, so which would be nice as well. And maybe additional status flags for exception handling, like say the divide by 0 occurs and you want to handle that exception. And are there any final questions?
I guess not. Very good job.